Hello, my friends. This is Miss Fairman. I am going to finish up the notes that we started on Tuesday. So it is our Chapter 5 Exponential Functions Part 1 notes, where we were factoring things with exponents. So I'm going to go through the examples and give you time to practice, and then you'll have all the notes. So you can go ahead and add these to the notes that you have from class. So let's start by looking at this example where it says factorize 4 to the x minus 9. So in order to factor things, I want to see if it fits into any of the patterns that I am used to. So first things first, how many terms are there? In this particular problem, there are 2 terms. There's a 4 to the x and a minus 9. And notice that 9 is a perfect square, so it makes me wonder, is 4 to the x a perfect square? Because if it is, then I have a dots. And if it's dots, I have a factoring pattern that I can use pretty easily. Well, yes it is. So 4 to the x is the same as 2 to the x squared. And 3 squared is the same as 9. So that is, in fact, a dots. And dots factors into the pattern a plus b, a minus b. So we would have 2 to the x plus 3, 2 to the x minus 3. And it doesn't matter whether you put the plus first or the minus first, but you do have to have one of each. Let's look at example B. Again, we're factoring, so I want to look and see how many terms I have. I have 3 terms. And here is where looking at this middle term gives me a good hint of how I could rewrite the first term in a different way. So I could write that as 3 to the x squared plus 4 times 3 to the x plus 4. So if I look at this, I have 3 terms, and this essentially is in the form of a quadratic, where the coefficient in the front is 1. So I am looking for factors of 4 that can combine to give me 4 in the middle. Or I can try and think of this, if this is a perfect square trinomial. Is the first term a perfect square? It is. Is the last term a perfect square? It is. And is the middle term the product of 2 times each of those perfect squares, where this part is, that last part is 2 squared. And it is. So we can use our factoring pattern. Since this is a positive, we would have 3 to the x, and then this value, plus 2 quantity squared, because it's PST. Or, if you didn't recognize that, the factors of 4 that combine to give me 4 are 2 and 2. So I would end up with 3 to the x plus 2, 3 to the x plus 2, which is the same thing. All right, go ahead and pause the video here and see if you can work out a few of these other examples. Now that you took a second, you can see the answers are here. Go ahead and check your solutions against my factored versions. And if you have any questions, pause the video again and ask one of your neighbors to help you. And if you still have questions, make a note so that you can ask me the next time I am in class. All right, let's move on to our next example. So now, instead of multiplying and factoring, or multiplying and undoing multiplying, which is factoring, let's talk about division. So in order to divide fractions, I have to have factors. So I have to have a common factor on the top and a common factor on the bottom. So here, I need to think about my exponent rules again. Remember, if I had a fraction like a over b, if all of that was raised to the n power, the n could be distributed to both of those parts. So if I start with my n distributed, I could work backwards and make it one fraction. So if I look at example A, I could rewrite this as 6 over 3 to the n power, and then I can simplify that fraction and make it 2 to the n, and that would be my simplified version. Another way to think about it is that if I have a product, so if I have 6 to the n, that's the same as if I have 2 times 3 to the n, which product rule tells me that I can distribute that n, so this would be the same as 2 to the n times 3 to the n. So I could answer it the way that I did here, or I could split up my numerator into 3 to the n times 2 to the n, and it's all still divided by that denominator of 3 to the n. And notice, now I have common factors of 3 to the n over 3 to the n. So that can eliminate, well, it doesn't really eliminate, it just becomes a 1. And I'm left with 2 to the n again. So either of those methods work to solve the problem. All right, using whichever method you want, you could look at B. I'm going to go ahead and write it as one fraction, so 4 over 6 raised to the n power. I can simplify the fraction to get 2/3, the whole thing raised to the n power. And then I could go back in and distribute that n power, so I would have 2 to the n over 3 to the n. All right, using those skills, go ahead and pause the video here and see if you can't simplify the problems in number 7. Okay, here are your answers. Check your answers against mine. Again, if you have questions, pause the video again, talk to a neighbor, see if you can figure it out. Let's move on to our next example. So in these examples here, we just had a monomial fraction, so one term over one term. In our next examples, we've got some fractions that contain binomials in the numerator. So again, in order to simplify, I cannot cancel out this 3n over 3n. No! Do not do that. In order to simplify fractions, you can only simplify factors. So we need to think about if there is a common factor inside that 6 to the n that we could then factor everything out. And we already talked about in the previous problem that we could rewrite 6 to the n. So we have 3 to the n plus 3 to the n times 2 to the n, and all of that is divisible by 3 to the n. So in my numerator, I can take out a 3 to the n, I can GCF it. That would leave me with a 1 plus 2 to the n. In the denominator, I have a 3 to the n. And now I can simplify these factors so that my final solution is 1 plus 2 to the n, or my final simplified expression. All right, let's look at example B. In example B, we have 2 to the m plus 2, so we can use our exponent rules to rewrite that as 2 to the m times 2 squared. So if we do that, if this first term is written like that, then in our numerator, we have a GCF of 2 to the m. So we can take out a 2 to the m. That leaves us with a 2 squared minus 1 in the numerator over a 2 to the m. Our 2 to the m's can cancel out, and that gives us 4, because that's 2 squared, minus 1, or 3. So 3 is our simplified answer. For part C, we're going to do the same process that we did in B. So we're going to have this thing here can be 2 to the m times 2 cubed. So we can rewrite that. 2 to the m times 2 cubed plus 2 to the m. And then the denominator is just 9. Well, if we GCF the numerator, we're going to have 2 to the m with a 2 cubed in the parentheses plus 1. All of that is still over 9. Well, what is 2 cubed? It's 8. Plus 1 is 9. So we actually have 2 to the m 2 to the m plus 9 over 9. What happens to those 9s? Bye. And we're just left with 2 to the m as our fully simplified answer. So using those examples as guidelines, go ahead and do the practice examples, and you can pause the video here to see how you did. Okay, here are your solutions. For number 9, I went ahead and wrote a few steps out. Notice that we have a 2 to the n and a 2 to the n for each of these terms. This is one term and this is a second term. So I GCF'd the 2 to the n on the outside, which meant that the stuff that was in the parentheses left over here and here, that formed its own parentheses. Combined like terms, the ones cancel out and I get 2 n's. Remember that 2 without an exponent is actually 2 to the 1, so we could rewrite it as 2 to the n plus 1 times n. Okay, that is the end of that section. Thanks for watching.